So hi and welcome everyone to the thesis defense presentation of my master student Muhammed Kirik. Today Muhammed Kirik is gonna present to us his thesis work. His thesis work is mainly focused on multiple input, multiple output with antenna number modulation. He particularly focused on solving the problem of not utilizing all the antennas in the case of using MIMO, the antenna number modulation. So we have this problem that in index modulation and number modulation, whether in spatial domain or spectrum domain, we don't utilize all the antennas. So he came up with new methods and technique that can make use of these inactive antennas in order to make the system as efficient as possible and don't waste any of the resources by utilizing these inactive antennas for far and near users in a very intelligent manner. So this is the things that he's going to be discussing, and I think Muhammed Kirik, you have 40 minutes to present your work to us in detail. After that, we are going to ask you questions about your work, starting from the external committee member, internal, and then myself. After that, we'll evaluate your performance and then let you know of your result. So with this, I think you can get started, and the floor is yours.
Okay, thank you, Hocam. First, can everybody hear me well?
Yes, we can hear you.
You can hear me, okay, great. So I'm starting then. Dear professors, dear friends, welcome to my thesis defense. My name is Muhammed Kirik, and I'm an electrical engineering student in the Department of the Electrical and Computer Engineering Department of the Graduate School of the Antalya Bilim University. And my thesis name is Multiple Input, Multiple Output with Antenna Number Modulation and its applications, as the Dr. Cihat Hoca just stated. So firstly, I will start with some brief introduction, and I will be doing some literature review, and then I will introduce my main contribution with this thesis. And all these will be taking about 40 minutes. So let me start with the introduction first. With the emergence of the wireless technologies, such as the Wi-Fi, 3G, 4G, and 5G, accessing to the internet services wirelessly is becoming the dominant way to access the data, as the wireless has almost the ubiquitous coverage. We can basically make the internet to reach everywhere with wireless technologies. And in addition to that, we can also achieve extremely high performances in terms of the data rates, low delay, and the ultra reliability. And all of these are coming with also the affordable costs. So as a result of that, the wireline-based communication technologies such as the ADSL or the fiber internet and the other wireline-based technologies, these are no longer competitive enough when we compare them with the wireless technologies to access the internet applications. And on the other hand, according to the scientists, they are predicting that there are almost 30 billion IoT devices actively serving on our planet. And when we consider the fact that this number was around 15 billion in the beginning of the last decade, it would not be really logical to not see the reality that these IoT devices are being a huge part of our lives, and they will have a transformational effect on our lives in the future as well. So even though this huge growth in the IoT devices brings a lot of excitement and hopes, because their possible application areas are so immense, such as the online banking, healthcare, electronic warfare, all of these are its application areas. But this uncontrolled growth also causes some concerns among the wireless communication scientists, because there are many concerns in this domain, such as the high power consumption of these devices, the reliability of the transmitted data, and mainly the security of the transmitted data and the spectral efficiency. These are all the problems that we should be concerning about. So the scientists work on these issues for years to produce a remedy for these problems, but um, we should find some logical solutions to eliminate these undesired effects without restricting the population growth of these devices, because there's no meaning if we just stop producing IoT devices and try to solve a solution to all of these problems. So for this reason, many types of different techniques have been adopted for years, and they are proposed in the literature. And in the next section, I will be talking about some of them. So the first technique that has been adopted for many years is the multiple input, multiple output systems. So it has great advantages, and its early development realized back in the 1980s and 1990s. It is basically a wireless technology that increases the data capacity by using multiple transmitting and receiving antennas. So in a MIMO system, the same data is transmitted through multiple antennas over the same path in the same bandwidth. And because of this, each signal reaches the receiving antenna through a different path, and this results in a more reliable data. And the multiple data streams also reduce the number of the lost data packages, which also results in a better data quality. But with all of these advantages, MIMO brings also some problems as well. The main problem of the MIMO that we have to overcome is the transmitter complexity, because when we are using multiple antenna elements at the both transmission and the reception sides, we are, if we consider this antennas to be resolved like one by one when we receive the data, this increases the complexity of the receiver. And the another major issue that we have to be dealing with in the MIMO systems is the interchannel interference. So we said we are transmitting the same data from different antennas to different receivers. So if we consider these arrows as the channels, we can see even on this figure they are tangling with each other. Even though this is an illustration, this is also a real life problem, and we call this the interchannel interference. This has to be resolved in the MIMO systems. So the other technique proposed in the literature is the massive MIMO systems. It is basically including all the benefits of the conventional MIMO schemes, but it is doing it with very, very large number of antennas, like 400, 500 antennas being used at the same time. So this provides us simultaneous multi-user services, because we have a lot of antennas and we cannot use them just for one person. So we are using it for multiple users, and it also has capability to exhibit superior performance in terms of the spectral efficiency. And since we are using a lot of antennas and sending the same data from many different antennas, we are having less propagation loss in our transmission systems. But with all these advantages, we obviously have some disadvantages as well. For example, the first one is the hardware and the signal processing costs. So we said we have 400, 500 antennas in the massive MIMO systems, and by deploying all of these antennas, we are basically spending money on the hardware. And we are also, when we use all of these antennas, we are also facing a problem that has to be solved, which is the signal processing and engineering. These are all the expenses that we have to be paying when we use the MIMO systems. Also, the radio frequency chain complexity is another issue in these MIMO systems. And lastly, the interchannel interference is still a problem in the MIMO systems, but it is even worse in this case because we have so many different antennas and so many different channels. So another scheme that has been offered in the literature is the multi-user MIMO systems. The main purpose here is to use multiple users in our transmission system, so we can serve them at the same time by using the same transmission system. So how we do this is we are creating a channel matrix where each user's data can only be pre-coded by that user's transmit antennas. So when we do that, we can basically serve different users, but in this case, we are having a disadvantage called the multi-user interference, the MUI. So the MUI is basically mixing the one user signal with the other user signal. And when we do that, basically the two signals of two users are mixing together, and they cannot come up with their intended received data. So this is a problem in the multi-user systems, but this problem can be resolved by using the multi-user detection techniques, which has been produced in the literature again in the uplink. But when we do that, we are increasing the receiver diversity, which is a trade-off in this system. So it's basically depending on the case when we need the multi-user cases. And another technique has been used in the literature for many years is the orthogonal frequency division multiplexing systems. They are mainly being used in the 4G and 5G technologies, and it is aiming to eliminate the inter-symbol interference by using the orthogonality of the signals. And by doing that, it offers more spectral efficiency because it is not using the guard interval that we are calling the cyclic prefix. So if I can show you that for 1 second. In the frequency division multiplexing systems, we are using the symbols, but to not mix them up, we are using a little bit space between each symbol. And when we do this, we are avoiding the ISI effect, but we are not using the spectra very efficiently because of this cyclic prefix. So when we not do that, when we don't put the cyclic prefix here, we are basically mixing the signals, and this results in the inter-symbol interference. So we don't want this. For this reason, we are using the orthogonality of each signal, and what we do here is making a symbol, and where it ends, we are starting a new symbol. So when they are orthogonal, they are not interfering with each other. We are avoiding the ISI, and we are also not wasting our spectra in our system. So this is why the OFDM is a good technique. So there are other techniques as well paired with the MIMO and the OFDM. So these are some of them: the spatial modulation, index modulation. So in the MIMO and the OFDM systems, we are in general using two different dimensions, the time and the frequency. But in these paired systems, we are adding also another dimension. And this third dimension allows us to transmit more data bits and use the spectra efficiently when we compare it with the conventional systems. So for example, in the figure 10, we have the index modulation. We are pairing this index modulation with the MIMO systems, and what we are doing here is basically creating a third dimension to transmit more data bits. And this third dimension, in addition to the time and frequency, is the indices of the active subcarriers in the system. So by doing that, we are transmitting more data bits, and we are improving our bit error rate performance in our system. And similarly, we have the subcarrier power modulation. This is similar. We are trying to add a third dimension, but in this case, our third dimension is not the indices of the subcarriers, but the powers of the subcarriers. And in figure 12, we have the subcarrier number modulation. It is also similar. We are trying to add a third dimension, but in this case, our third dimension is number of active subcarriers that we are transmitting our data. So by exploiting the number of the active subcarriers, we are we are transmitting more data bits and improving our bit error rate performances. So this brings us to the multiple input, multiple output system with the antenna number modulation. This is the one that we have proposed in the last year as a research paper. And this was also my senior project in my bachelor year. So I will talk about this now. What is the multiple input, multiple output with the antenna number modulation and the adaptive antenna selection? It is basically a novel transmission method that allows us to transmit additional data bits by the number of the antennas in the MIMO system, while it also allows us to send the data bits from the specific antennas that can offer the highest channel quality. So why do we want to use this system? Because it allows us channel and data dependent antenna selection in our MIMO system, which is not something that the other schemes in the literature can achieve, because they are forcing the indices to be used in their systems while we are using the numbers. We never say which antennas to be used. So it gives us a little bit more freedom to transmit our data for the transmission. So it also allows us more reliable data because of this antenna selection feature. And we can also achieve more spectral efficiency when we compare it with the conventional plain MIMO schemes. So we have the system model here for the antenna number modulation. In the figure 13, you can see that we have an incoming bits group, and we are dividing these incoming bits into two different groups as the antenna number modulation bits and the signal constellation bits. So here we are using the conventional data transmission techniques such as the BPSK, QPSK, QAM, any modulation technique that has been conventionally used in the literature. And in this part, we are using the antenna number bits. These bits are used to decide how many antennas will be activated in our system. So in this case, we have 4 antennas, and to decide how many symbols will be used in the antenna number bits, we have a small formula here. The N2 equals to log 2 in T. T is 4 in this case, so we have two bits in each ANM bit symbol. So since we are using BPSK here, we are using 1 bit in our symbols. So for the transmission of 1 symbol here, we are exploiting 2 symbols here, and we are transmitting these 2 symbols by using only 1 spot in our spectra. This is the main logic of this scheme. And this is the receiver structure of the proposed antenna number modulation and adaptive antenna selection. We are demodulating the main bits and the ANM bits group separately, and to do that we are using a ML detector, the maximum likelihood detector, and eventually we are coming up with our receive bits. So to understand the concept better, we have an example here. Let's have a quick look at it. So imagine that we have this incoming bits group and we want to transmit this by using binary phase shift keying modulation, which means that we are going to be having 1 bit in our each symbol, and we have 4 transmit antennas and 1 receive antenna. The reason why we are using 1 receive antenna at the reception site is because we want to keep the process simple and make it understandable for everyone, and we can compare it with the other schemes in the literature in a better way. So we have 4 antennas. So to decide how many symbols we are going to have for each transmission of this main bits, we are applying the formula that logarithm in 2 bases t equals to 4. So we have 2 here. So which means that we are going to have 2 bits in each ANM bit symbol. So we are transmitting this 1 by using this 0, 1. And if we come back to our mapping table, we can see that this 0, 1 here means activation of 2 antennas in our 4 antenna system. And there are 6 different possibilities to activate 2 antennas in a 4 antenna system. And we are deciding which antennas will be activating by checking their channel coefficients. So we can pick the highest one, and we can improve our data transmission and the bit rate performances. So for simplicity, we consider that we are activating only the first 2 ones. So if we come back to our figure, we have 1 here and we have 0, 1, which means the activation of 2 antennas. So we are transmitting this 1 by using these 2 antennas. And in the second case, we have a 0 and we have a 1, 0 here. If we come back to our table, we can see that in the ANM mix group, when we have 1, 0, it means we are activating 3 antennas in our system when we have 4 antennas in total. So again, we never say which 3 will be activated. We have 4 different possibilities to activate 3 antennas in a 4 antenna system. But let's just for simplicity pick this one. We are activating the first 3 antennas. And if we come back here, we are transmitting this 0 by using the first, second, and the third antenna. So in total, we are using 3 antennas to activate this 0. And lastly, we have this 0. We have another 0 to transmit. And when we come here to see the ANM bits group, we have 1, 1. We are coming back to our mapping table. We have when we have 1, 1, it means we are activating all the 4 antennas in our system. So we are transmitting this 0 by using the first, second, third, and fourth, basically all of them. So when we apply this scheme on the MATLAB and simulate it, we get these results. As you can see here in the blue line in the figure 17, we are achieving a beta rate performance between 10 to the minus 3 and 10 to the minus 4, which is an impressive beta rate performance. And in the figure 18, we have the comparison of the proposed scheme. In the red line, we have the spatial modulation, the beta rate of the spatial modulation that I just mentioned. And it is performing between 10 to the minus 2 and minus 3. And we have in the blue line the antenna number modulation scheme. But the reason why we don't get a good result in this blue line, because we are not applying the adaptive antenna selection. We are not dictating our system to use the antennas that can offer the highest channel capacities. We are just picking them from beginning to the end without doing any channel capacity order. But in the black line, we are making the antenna number selection, and we are sorting our antennas from the highest quality ones to the lowest quality ones, and we are using the ones that can offer the highest channel capabilities. And when we do that, as you can see, the beta rate performance of the proposed scheme is outperforming both of the spatial modulation and the antenna number modulation without the adaptive antenna selection. So this was our first research, and after that we wanted to do take our research further and increase the number of the antennas and turn them into a different concept. We tried to add a third dimension in our system by using the antenna number blocks. So for this reason, we came up with this research, the multiple MIMO with the antenna number modulation and the adaptive antenna selection. And now I will be talk a little bit about this and we will move on. So we have the transmitter structure of the multiple MIMO-ANM scheme. And in the figure 19, you can see that. The procedure is quite similar with the antenna number modulation. We have the incoming bits, and we are dividing it as the main bits and the antenna number bits. These main bits are modulated by the conventional data modulation techniques such as the BPSK, QPSK, QAM, any of them. And the antenna number bits are deciding how many antennas will be activated. But in addition to these two that we already had in the antenna number modulation, we are adding also a block number bits. These are responsible to decide how many blocks in the data transmission system will be activated. So we have these blocks, the B1, B2, B3, and B4. Each of them are containing 4 antennas, and in total we have 16 antennas in our system. So we are using more antennas. And when we come here and see our tables, it's a similar table with the antenna number modulation, but we have 2 different tables now. One for the block number modulation, for the block numbers, how many blocks will be activated, and one for the antenna number activations, how many antennas will be activated in each active blocks. So when we have the 0, 0 in the BNM bits group, we activate only one block. When we have 0, 1, we are activating 2 blocks. When we have 1, 0, we are activating 3 blocks. And when we have 1, 1, we are activating 4 blocks. And similar for the ANM bits group, we are activating for the 0, 0 only one antenna, 0, 1 for 2 antennas activation, 1, 0 for 3 antennas activation. And when it is 1, 1, we are activating all the 4 antennas. So we have this table, table 4. It shows some of the possibilities of the antenna and block activations. So we can take a look at this one for understanding the concept better. So in the BNM blocks, we have 0, 1, and in the ANM blocks, we have 1, 0. So which means that we are activating two antenna blocks, and we are activating 3 antennas in each of these antennas, each of these antenna blocks. So if we come here, let's just say we are not doing any adaptive antenna selection or block selection. So we are just picking these two for the antenna number activation, because what we said here was we have 0, 1 in our block number bits, and 0, 1 means activation of 2 antenna blocks. And we have 1, 0. So when we have 1, 0, we are activating 3 antennas in each active block. So let's say we are not doing any adaptive antenna selection, so we are activating these 3 directly. So this is how the antenna activation works in the multiple MIMO-ANM system. And to understand the concept better, we can look at this example. Imagine that we have this incoming data bits, and again, to transmit our data, we are using binary phase shift keying. So in each of the main bit symbol, we are going to be having only one bit, which are separated with different colors. And when we imagine that we have 4 antenna blocks as given in this figure, we are going to have a similar formula to how many antenna blocks block bits we are going to have in each symbol, which is logarithm 2 b equals to 4. So we are going to have 2 bits in each symbol as stated here with different colors. And similarly for the antenna number bits, we are going to put a t here in the logarithm, which is also 4. And we are going to have 2. The reason for that, because we have 4 antennas in each block. So when we do this, what we are coming up here is as follows. So we want to transmit this 1 by using this 1, 0. If we come back to our table, 1, 0 means we are activating 3 blocks. And we have also a 0, 1 in the ANM bits part. So 0, 1 means activation of 3 antennas in each subblock. So we have this variable table because we don't want to just use the antenna numbers, but we also want to pick the ones that can offer the highest channel quality. So these are the randomly generated antenna coefficients, and when we look at the absolute values of them, we can see them as the H values. And this part gives us the block coefficients of the MIMO system. So when we look at it, we can see that the highest one is this one, the second highest is this one, the third highest is this one, and the fourth highest is this one. So which means that we are going to be activating the B4 first, then B3 and B2 and the B1. And when we look at each of the blocks, look at in them, we can see that the highest channel coefficient of an antenna is the T14 in the B4, T15, and we have the T14. And when we do the same thing for the B3, we can see that we have the T11 and T12. And in the second block, we have the T5 and T6. So we are activating 3 blocks, and we are activating 2 antennas in each of these active blocks, and these antennas are stated as you can see in the figure. So if we look at the illustration in the figure 22A, we can see how we are activating the antennas and blocks. we said we are going to be transmitting 1, and we said our BNM bits are 1, 0, which means we are activating 3 blocks, and we just see that the highest channel coefficient offering blocks are the B4, B3, and B2. We are activating this. We are not activating this block. And since we had 0, 1 in our antenna number modulation bits, we are activating 2 antennas in each active blocks, and we just saw how many, which one of them are providing the highest channel capabilities. So we are activating the T15, T14, T11, T12, and T5 and T7 in each of these B2, B3, and B4 blocks. And similarly, we are transmitting this 0 by using 1, 1. 1, 1 means 1, 1 means activating 4 blocks, and 1, 0 means activating 3 blocks, 3 antennas in these active blocks. So when we see this figure, we are transmitting the 0, we are activating all the 4 blocks, and we are activating 3 antennas in those active blocks. And lastly, we are transmitting the 1. We have 0, 1 in the main bits group, the BNM bits group, which means activation of 2 blocks, and we have 1, 1 in the ANM bits group, which means we are activating all the 4 antennas in the active subblocks. As you can see here in the figure 22C, we are activating 2 blocks, which are providing the highest channel capabilities, B4 and B3, and we are activating all the antennas in them. So at the receiver, we are basically adopting the same receiver structure as the plain MIMO-ANM. We are demodulating the antenna number bits by using a maximum likelihood detector, demodulating the main bits. But in addition to those, we also have another bit group which we call the block number bits. We are also demodulating it by using a maximum likelihood detector, and eventually what we are coming up with is our receive bits. So when we do this on MATLAB, these are the results we get. As you can see stated in the pink color, we are having this beta rate result. And when we compare it with the figure 25, you can see that it is performing a better performance when we use the fourth dimension, when we use the block numbers as a fourth dimension, and when we use 16 antennas. And it even outperforms the performance of the antenna number modulation with the adaptive antenna selection when we use 16 antennas in it. So we can prove by that the block number modulation is working well as a fourth dimension to transmit more data bits. So after this point, we are now introducing the main contribution of this thesis, the multi-user application of the multiple input, multiple output systems. So now I can talk about it. The main concern of us here is to serve 2 users at the same time. Because if I come back here in this figure here, for example, for the transmission of 1, we said we have 0, 1 here, and 0, 1 means the activation of 2 antennas. So we are activating these 2 antennas, but these 2 antennas are remaining without any job. They are not working, they are not doing anything, but we want to exploiting the performances of these 2 antennas. So for this reason, we are proposing a new technique, and by doing that, we can include another user, and we can serve that user as well, even though we don't have the same service quality for that user. We can still serve that user, and we can exploit the all capability of our system. So in this case, we have 2 users. One of them is located in a far location to our transmitter, and one of them is located in a near location to our transmitter. And our main concern to serve is our far user. So we are applying the antenna number modulation technique on this far user, and we are only serving the near user by using the remaining antennas that remain from the far receiver's data transmission. So for the far users data, we are again splitting the bits into two different groups as the main bits, which are modulated by the conventional modulation techniques in the literature. In this case, we use BPSK. And the other group is named as the ANM bits. This part is deciding how many antennas will be activating. And it is also, as we said earlier, doing the adaptive antenna selection. So it is also sorting the antennas based on their channel capacity orders. So after doing this, we are deciding which antennas are proposing the high quality and which antennas are proposing the low quality. And we are transmitting these main bits, which are modulated by the BPSK, by using these high quality antennas. And we are transmitting the data in the main bits group by using a high power, because the user is in a far location and we want the data to reach there. But in this case, when we have the near receiver, we are again modulating the data by using the BPSK, but we are using the low quality antennas because our priority is not the near user. We are just serving that user so we can keep our all antennas busy. And to do that, we are using a low power because we don't want our far user to be affected by the data. Because when we use high power for the near receiver, uh, his data will be reaching to the far receiver as well, and this will result in having the MUI effect, the multi-user interference effect, and we don't want our far user to be affected than that. So we are using low power here, and we are basically concluding our transmission. And we have an example here again, so we can understand the concept better. Imagine that we have this data bits group for the far receiver, and we have this data bits group for the near receiver. And we are again using BPSK in this case. So in each symbol, we are transmitting 1 bit. And we have a 4 antenna system. So when we have 4 antenna, we already said that we are having 2 bits in each ANM bit symbols. So for each bit here, we have in the main bits group, we are going to be looking at 2 bits in the ANM bits group. So if we look at it, we want to transmit this one by using 1 0. So 1 0 means activation of 3 antennas. So there are 4 different possibilities to transmit this one by using 3 antennas. And let's just assume we defined our channel capabilities as the H1 and H4 and H2 and H3. So the first antenna is offering the highest channel capability, so this is our first priority to enable, and the fourth and the second and the third. So when we look at it, we can see that we can use this case. So we can activate the first, second, and fourth. So if we come here and look at the figure 28A, as you can see, we are using the first one and the fourth one and the second one to transmit the far user's data. But since the H3 is the T3, the third antenna is offering the lowest channel capacity, we are using this to serve a near user that we named as Natalie. And we can look at another example here. For example, let's say we want to transmit this 1, and we are seeing the fourth symbol. So the fourth symbol is stating that we have a 1 1 here. So when we look at this 1 1, we see that we are transmitting this 1 by using all of the 4 antennas. So if we look at the figure 28D, we can see that we are activating all the 4 antennas to transmit the far user's data. But in this case, unfortunately, we don't have any chance to transmit the near user's data, which is okay because Our first priority was never to serve the near user. Our first priority is always to far user and keep all the antennas busy. And in this case, we use all of the antennas, and it's okay to not serve the near user. This is part of the system model of the multiple user ANM scheme. So at the reception, we have two different receivers now. One of them is for the far receiver and one of them is for the near receiver. So for the far receiver, we don't have any change from the plain antenna number modulation, because what we just said is that we are using a low power for the near user. And for this reason, the signals of the near user are not reaching to the far user. And the reason for that is because we don't want our far user to be affected by the multi-user interference. And this is exactly what we do. So since the far user don't get the signals of the near user, we don't have anything to worry about. We can directly apply the receiver structure of the plain antenna number modulation. But on the other hand, we have the receiver structure of the near user. As you can see here, this near user is both in the red zone, which is her own data, and she is also in the green zone, which is the far user's data. So she's capable to receive all of these data. So we have to extract this data from the whole data to reach to the pure near user's data. So for this reason, we are firstly decoding the far user's data by using the BPSK demodulation, and we are extracting it. And after that, we are using a successive interference cancellation. And eventually, we are getting the near user's data. And when we demodulate it, we are coming up with the near user's received data. So this is how the receiver structure of the near user works. So when we apply this scheme on the MATLAB, we come up with these results. This is the data, the beta rate performance of the far users data. As you can see, given in the blue line, we are achieving something between 10 to the -3 and -4, which is the same beta rate performance of the antenna number modulation without the multi-user. So which in this case, we can say that we are not degrading the beta rate performance of the far user somehow. And in the figure 32, we are comparing the beta rate performances of the far user and the near user. As you can see, the near user's data, which is given in the red line, it is not capable to perform the same beta rate performance as the far user, because first we use the low quality antennas for this user, so we are not using our best quality antennas. And in addition to that, in some of the cases, for example, when we use all the 4 antennas for the far users, we are not serving this near user. So it is pretty normal for the near user to get a low beta rate performance. So in the next section, we are taking our scope from the MIMO, and we are focusing on the OFDM systems. And again, we are looking at a multi-user technique, but in this case, we are doing this on a subcarrier number modulation. So in this case, we have this transmitter structure for the subcarrier number based OFDM scheme. Again, we have M bits for the far user, and we are putting this M bits into the bit splitter. And in this case, since we are using OFDM system, we need subblocks. So we are dividing the M bits into G different subblocks, and each of these subblocks we have P bits, and these P bits are divided as the P1 and P2. The P1 is the SNM mapper, and P2 is the conventional MRE modulation techniques proposed in the literature. This is pretty much same as the antenna number modulation, but in this case we are only using the subcarriers because we are in the OFDM base. So after doing this separation for each subblocks, we are sending them to the primary OFDM block creator. And on the other hand, we also have a near user here. So we are also modulating this near user's data by using the conventional modulation techniques. And we are transmitting them by using the inactive antennas that we did not activate it for the far user's data. So we are here taking the complement of the SNM mappers. So if we look at this table, it's the similar procedure as the antenna number modulation. When we have the 0, 0, we are activating only one subcarrier for the far user. And these remaining 3 subcarriers are closed for the far user. But for the near user, we can actually make a use out of them. So we are activating them for the transmission of the near user's data. Similarly, for the 0, 1, we are activating 2 subcarriers, and the remaining 2 subcarriers are exploited for the transmission of the near user's data. And for 1, 0, we are activating 3 subcarriers, and the remaining one is activated for the near user's transmission. And again, for the 1, 1, we are activating all of the subcarriers in our subblock, and none of the subcarriers is used for the near user, so we don't serve to the near user in this case. So this is another example. So imagine that we have these subcarriers, 4 subcarriers, and we have the far user's data M and the near user's data N. So let's say we have the 1, 0 for our subcarrier activation mapper. So when we look at the figure at the table, for the 1, 0, we are activating 3 subcarriers. So we are activating these 3 subcarriers to transmit this 0 to the far user. And if you notice that the amplitudes of these subcarriers are higher than the 4th subcarrier, the reason for that is because we are using a high power to transmit our data to the far receiver. And we don't want the near user's data to reach there to the far receiver. So for this reason, we are using a low power for the near receiver subcarrier. And when we do that, we are basically completing our data transmission. And the detection for the far user reception side is similar as the conventional MIMO-ANM. But we are using the OFDM receiver in this case. So we are basically doing the analog to digital converter and removing the cyclic prefix and performing the fast Fourier transform. And after that, we are demodulating the subcarrier numbers and the transmitted symbols separately, and eventually we are coming up with our received bits. So when we do this on the MATLAB, we get these results. The figure 36 shows the bit error rate performance of the far user, and figure 37 shows the bit error rate performance of the near user. As you can see, when we look at the figure 36, we can see that when we use the binary phase shift keying for the transmission of the far user, we can reach a point between 10 to the minus 4 and minus 5. And for the near user, when we use the BPSK modulation for the transmission, we can reach to a point between 10 to the minus 3 and minus 4. As you can see, the near user's achievement in terms of the bit error rate is worse than the achievement of the far user. And this is again pretty normal because this was what we were aiming. We were trying to serve two users, and we are trying to make our far user our first priority. So we are using the subcarriers that can offer the highest channel coefficients for the far user. and we are only using the lower ones for the near user, and in some of the cases we don't even serve the near user. So this was it with my presentation, and if you have any questions now, I can answer them. Thank you.